Hello friends, this lesson is all about heat transfer in various processes. The previous lesson was related to first law of thermodynamics and the before that we discussed about the specific heat. Before going through this lesson, just go through those two important lessons, that is specific heat and the first law of thermodynamics. We have already discussed the work transfer in various processes, like there are five important processes, that is constant pressure, constant volume, constant temperature, adiabatic and polytropic. In all those five processes we have discussed the work transfer. So if you face a question to calculate the heat transfer in these various processes, how to calculate the heat transfer in constant volume, constant pressure, constant temperature, adiabatic, polytropic, so we're gonna discuss all these five processes in detail in this particular lesson. Fine, just keep in one important point. Whenever you will transfer heat, temperature will obviously increase, right? Whenever the heat will be transferred, temperature will increase. But there is one very important process. Whenever you will supply the heat to that particular process, the temperature will decrease. That is the polytropic process. In polytropic process, whenever heat is supplied, the temperature will decrease. This is because of the polytropic specific heat. And regarding polytropic specific heat, I have already discussed it before. Right, but before proceeding further, I would like to introduce myself. My name is Harshit Agarwal. This is all about me. You can always rate, review, recommend, and share this lesson. You can also follow me on this specified link. So, to start with, before going through these five processes, one thing I want to mention is the convention of heat transfer. Like we have discussed the convention of work transfer, work done by the system is taken as positive and work done on the system is taken as negative. Similarly, heat supplied to the system is taken as positive and heat rejected from the system is taken as negative. Keep this convention in your mind. I'll be solving all the numerical problems related to this particular convention. Heat supplied to the system is taken as positive and heat rejected from the system is always taken as negative. Next, what is enthalpy? See, enthalpy is nothing but to make the thermodynamics easier so that you can learn the important terms. In thermodynamics, the term U plus PV, that is internal energy plus pressure into volume. This particular term was appearing very frequently in steady flow energy equation, right? So to make thermodynamics easy so that you can solve the numerical problems, U plus PV were given the name of enthalpy, and that's why there is steam tables related to enthalpy at different pressure and temperature. Just keep in mind U plus PV is equal to enthalpy. It is an extensive property. See, internal energy is a property. Enthalpy is also a property. Like internal energy is an extensive property, specific internal energy is an intensive property. Similarly, enthalpy is an extensive property, specific enthalpy is an intensive property. Specific enthalpy, that is small h is equal to capital H by m, is an intensive property. Enthalpy is an extensive property, specific enthalpy is an intensive property. Now we will discuss the heat transfer in various closed system processes. First one is constant volume process. We will start with the equation of first law of thermodynamics. In constant volume process, the first law of thermodynamic equation is dq is equal to du plus pdv. As we know that in constant volume process, the value of dv is equal to 0, that means pdv is equal to 0. So heat transfer in constant volume process is equal to change in internal energy. Always keep in mind, whenever anyone asks you to calculate the heat transfer in constant volume process, that is dq is equal to du, that is heat transfer in constant volume process is equal to change in internal energy. That is why we can write du is equal to mcv dt. Always write du is equal to mcv dt because dq is equal to du और du जो है ये कांस्टेंट वॉल्यूम है तो cv जो है स्पेसिफिक हीटेड कांस्टेंट वॉल्यूम होगा तो dq is equal to du for constant volume process. Heat transfer in constant volume closed system process is equal to change in internal energy. This equation is valid. Keep in mind this equation is valid for any working fluid, whether it is steam, water, gas, etc. Second one, constant pressure process. Again starting with the first law of thermodynamics equation, dq is equal to du plus pdv. We can write dpv And if we will open it, we can write it as PdV plus VdP. It is a constant pressure process, so we can cancel out at VdP. So the equation remains dq is equal to du plus PdV. So we can write it as dq is equal to du plus dPV. Taking d out, we can write it as dq is equal to u plus PV. हम इस इक्वेशन को u प्लस पी वी लिख सकते हैं. व्हेन वी विल ओपन इट, इट विल बी डी यू प्लस पी डी वी प्लस वी डी पी. वी डी पी कैंसिल हो गया तो अल्टीमेटली यही रह जाएगा. It will come out to this, and we know that enthalpy is equal to u plus PV. That means dq is equal to dH. Whenever heat is transferred at constant pressure process, it will be equal to change in enthalpy. For constant volume process, it will be equal to change in internal energy. For constant pressure process, it will be equal to change in enthalpy. Heat is transferred in constant pressure closed system process is always equal to change in enthalpy, whereas heat transfer in constant volume process is always equal to change in internal energy. For constant volume, change in internal energy. For constant pressure, change in enthalpy. These are some of the important assumptions. Closed system, potential and kinetic energy is negligible. For reversible, obviously, because we have used the reversible equation. Second, constant temperature process. As I have already told you, Joule experiments show for ideal gas, internal energy is a function of temperature. Internal energy is a function of temperature. As the process is constant temperature process, T is equal to constant. Temperature is equal to constant, that means internal energy is equal to constant. U is equal to constant, that means du is equal to 0. Temperature is equal to constant, internal energy is equal to constant, that is du is equal to 0. Change in internal energy is equal to 0. From the first law of thermodynamic equation says dq is equal to du plus dw. Temperature is constant, internal energy constant, that is du is equal to 0. Du is equal to 0, so heat transfer is equal to work transfer. Whenever heat is supplied in constant temperature process, dq is equal to dw. Heat supplied in constant volume process is equal to change in internal energy. Heat supplied in constant pressure process is equal to change in enthalpy. Heat supplied in constant temperature process is equal to work transfer. If for an ideal gas undergo isothermal process, heat transfer is equal to work transfer. Heat transfer is equal to work transfer. Fourth, adiabatic process. Whenever heat is supplied in adiabatic process, dq is equal to 0. So we can write it as dq is equal to 0, dw is equal to minus du. For adiabatic process, heat transfer is equal to 0. See, there are 5 processes: constant pressure, constant volume, constant temperature, adiabatic and polytropic. Whenever you will supply heat in any of these processes, temperature will increase. But there is one process in which the temperature will decrease. That is the polytropic process. And I have already explained you the reason for that thing while discussing the polytropic specific heat. See, if you want to get the answer for heat supplied, dq is equal to du plus dw. We know the value of dw is P1 V1 minus P2 V2 upon n minus 1. So we can write work transfer is equal to P1 V1 minus P2 V2 upon n minus 1, and du can be written as U2 minus U1. Heat supplied is equal to mCV T2 minus T1 plus P1 V1 minus P2 V2 upon n minus 1. In place of CV, we can write R upon Ga minus 1. So Mr T2 minus Mr T1 can be written as P2 V2 minus P1 V1. Mr PV is equal to MRT ideal gas equation. So P2 V2 is equal to Mr T2. For Mr T2, we can write it as P2 V2. For Mr T1, we can write it as P1 V1. So dq is equal to P2 V2 minus P1 V1 upon Ga minus 1 plus P1 V1 minus P2 V2 upon n minus 1. So taking out P1 V1 minus P2 V2 upon n minus 1, it is minus n minus 1 upon Ga minus 1 plus 1. So P1 V1 minus P2 V2 upon n minus 1 is equal to work transfer in polytropic. It is 1 minus n minus 1 upon Ga minus 1. So heat transfer in polytropic process is equal to work transfer in polytropic process. Gamma minus 1 in numerator में आएगा, in numerator gamma minus 1 minus n plus gamma. So heat transfer in polytropic process is equal to gamma minus n upon gamma minus 1 into work transfer in polytropic process. This is the value of heat transfer in polytropic process, right? And the value of polytropic process will tell you whenever heat is supplied in polytropic process, temperature will always decrease. Just go through that particular slide there. So these are the important formulas. let me tell you once again, whenever heat is, if anyone will ask you what is the heat transfer in constant volume process is equal to change in internal energy, heat transfer in constant pressure process is equal to change in enthalpy, heat transfer in constant temperature process is equal to work transfer, heat transfer in adiabatic process is equal to 0, and heat transfer in polytropic process is equal to gamma minus n upon gamma minus 1 into work transfer in polytropic process. These are the assumption. Closed system, reversible, potential energy and kinetic energy are negligible. Just go through these slides. If you have any queries, you can ask me that in the comment section. Thanks a lot from my side. This is Harshit Agarwal.